All right. So today we're going to be writing a very simple program for this processor that creates a sort of marquee effect on port B, which just means alternating the bits on port B between 55, which if we go to binary, you see that's 10101001, and so there would be like 10 right up there if we increased our thing once. Between 55 and AA, which is just the opposite filled. So where we had a 0 before, now we have a 1. And so in order to make this, you can see right here, we have our program editor and our default instruction reset vector. All of that's already set up. I have now added in. So what we really need to do is just figure out a way that we can set port B to a value. Now, right now, port B does not have like capabilities for inputs or outputs, so we can simply write to it, and whatever we write to the correct memory address for port B will show up right there. So the first thing that we want to do is, because we want to alternate between this 55 and AA, we need to somehow get the number 55 into the memory. And so here's our 55 hex, which is 85 decimal, or that in binary. And you can see if we hit these up and down arrows, it basically gives us like 0 padding so that we can see all 8 bits kind of like indexed correctly. But here's our 55, and we have to somehow get that into the memory. So what we're going to do is we're going to use an immediate command. So if I show all of these are color coded based on like what kind of opcode they are, like what they do. And so in order to get something into our computer, you see here we have the A register, the X register, and the Y register, right? So we could actually load something into this A register if we wanted. And that's what we're going to do. So in order to load, let's just grab this little slider here and drag it up to load so that only these red ones that were in show all, so you see when we hit show all, these are red, they're the load ones. When we move this to load, it just highlights all of those. So we need to load our value 55 into the A register. And the way to do that is using a immediate opcode. And so those are any of these with these little hashtags right down here. The load Y hashtag, load X hashtag, and load A hashtag. Well, since we're going to be using the A register, we're going to want this A9 opcode. And you can see once we grab it, we're able to pick it up, move it around. We're going to place it into our program right here. And now we simply need to put in the byte that we want to load into the A register, because you see all of these values are coming out in hex except for this flags thing. But with all of these coming out in hex, basically each of these can store 8 bits, 1 byte of like a value basically. So in our A register, we want to put in 55 hex, which we had already discussed is that value and a decimal value as well. And so when we hit create, now we have a number that we're able to also put into our program. And so now if we simply ran this program, you would see that 55 gets loaded into A. So in order to do that, let's hit upload to EEPROM, and that puts it into the EEPROM part of the computer right down there. Now in order for this program to run, we need to first reset the processor, and then we will tick the clock. So on our first tick, you can see that our opcode is now A9, because at program counter 8000, that was what it had already read in basically. At 8000, it had read our opcode A9, which we had put into there. And so you see it also doesn't have an operand or anything available yet, so that's okay. We're just going to tick it one more time. And now we're at 8001 is what we had just read, so our program counter automatically incremented to get to the next one. But you can see our operand low was 55, because our operand for immediate is only 1 byte. And so that then got loaded into the A register. So that command was successful. Wonderful. So if we hit reset now, you'll see it resets our program counter back to 0. It doesn't mess with anything else on the processor though, so we do have to be careful in case like we were expecting something to be 0 from the start. But since we're not, now we just want to go and put this out on port B, right? So in order to do that, we need to somehow take this A register and store it out to the memory, because you see our processor, the registers are all a feature of the processor, and then all the rest of this, the RAM, the VIA, versatile interface adapter, which is what our ports are connected to, and the EEPROM, which is what it's been reading this program from, they're actually all connected just to a memory location. They're basically mapped to memory. And so what we're going to do here is we need to store our value from the A register out into the memory. And in order to do that, we do have a command right here, or an opcode. It's 8D, and that is store A. And you'll notice that the mode, the addressing mode is what this is called, is absolute, which means that whatever number we put after this is going to be the absolute address that it stores our A register to. So let's put that into our program. Now we need to think about this address for a second. The way that our processor is mapped out, we have basically 0 to 100 in hex, or 0 to 256 decimal is our like 0 page memory. And then beyond that, we have, I believe it's like 100 to 1FF, maybe. Yeah, so then 256 to 512, I guess, or 256 to 511 is our stack. And that's what our stack pointer handles. And then beyond that, that's just general purpose memory. And our memory bus is able to accommodate 2 bytes of data, which means that we can address memory all the way up to FFFFF, or 65,535. I'm just going to throw this away really quick. Doink. Now, our EEPROM is a 32K EEPROM, and it's mapped to the upper half of this address space, which means that it's mapped to everything 8,000. Sorry, I'm just going to clear that because I'm not sure if I hit the decimal. 8,000 and up. There we go. Yeah, I was in decimal mode. Okay, so 8,000 and up is everything above 32,768. And you can see that that's reflected in our reset vector right here. Now remember that this is little endian, which means that instead of having 8,000 be 8000, it's 0080, because the 00 is like this less significant byte. So the less significant byte comes first in little endian. If I didn't misspeak there, I might have described that wrong, but that's generally how I think about it. So anyway, that's everything above this number. Well, in between, there's definitely some RAM in there, but then there's also this VIA, and that happens to be attached to hex 6000 is where the VIA starts, and that's 24,576 in decimal. So what we need to do is basically write to 6000 in our memory in order to store this. So in order to put that in, we were just talking about little endian format here, right? So let's go back into hex, right, and clear this out. If we put in 2 zeros, it's already 0, it doesn't matter, but here's a 0. And so we can put that in first, just like our reset vector in little endian. We're going to put that into the first bit of our memory, or the first byte that we're going to store it into. And then we have 6,000 is what we need. And so you can see here how like 8,000 is 0080. So 6,000 is just going to be 0060. And we put those two in. And now hopefully when we run this program, it will actually store our value 55 out onto port B. And that's going to take 1, 2, 3, 4, 5 clock cycles. So let's see how that goes. Let's upload this to the EEPROM, and then reset the processor, and then tick it once. Shoot, I might have ticked it a couple times. Yeah, I did. Okay. Let's tick it once. So you see it just flashed once nicely there. And so it read A9. And then our operand, remember, it's still like thinking of the operand from before. So that's why it's already 55. But if we tick it again, you'll see now it's 55 and it's stored it into the A register. And then we can move on now. So now we will be moving on to 8D when we tick it. And you can see now it gets opcode 8D, and it hasn't yet seen the new operands, but now at least it's thinking about 8D, right? So then it sees our low order, which is 0, 0, and you can see operand low went to 0, 0, right? I'm not sure exactly why high is displaying 4 bits here. We'll, or 2 bytes. We'll figure that out in a minute. But let's tick it again. And now we can see that 60 is loaded into our operand high. And so then it basically just combines those into the operand, and then it stores our value. And you can see because we put in 6000, it stored it right out on port B. Isn't that wonderful? So that's how our program is working so far. So I'm going to reset our processor again, go back to 0, and we can continue building it. So now we want to alternate to the other option, basically. And that is if we clear this out, so we have 55 right here. And if we click it like that, it starts with a 0, right? So we want one that's going to start with a 1. So let's do that. 1, 0, 1, 0, 1, 0, 1, 0. And that should be AA in hex if I entered it right. And it is. So what we're going to do is we're just going to make that. And then just like before, we need to load that into our A register again. And that's going to overwrite what's already there. So let's get out a A9. Didn't grab it right. There's an A9. And put that into our program, and then put our AA into the program. And I'm just going to throw away this B9 while I'm at it. Great. Now, we need to store it once again out to port B, and you can see that that's actually going to be really easy. We can just copy that exact same thing we already did there. So we're going to store A in absolute addressing mode. Let's clear this out so that we get some zeros. And then enter 60 hex. Take that out and put it there. And now our program should display this marquee effect. So let's upload it to the EEPROM and give it a try. So we're going to tick it once. We can see it gets A9. Tick it again. Now 55 is loaded into the operand. So we've loaded then into the A register 55. We see 8D in there. And then our operand changes to 0, 0 on the next tick. So we're looking at right there again. Then we get 6000. That's like our full operand all put together. And you can see it has stored it out to port B. And now it's time to load the next thing into our A register. So when I tick this, we once again get A9. And then our operand this time is AA. See that? So there's our operand low is AA, which is great. And then we're going to then tick it again. We should get 8D. There we go. And then 0, 0. Yep. And then 6, 0. And it stores it out, and you can see that it's changed then. Now, if we keep on ticking this beyond here, do you see how it's reading EA? That's the opcode. If we come looking over here, it should be under other. In fact, it's the only one under other. It is no op. And it's implied, so it has no operands at all. But no op just means it's going to skip this clock cycle. And so what we could do is we could just keep on ticking the processor here, and no matter what program counter we got to, it would just keep on reading EA and not doing anything. And so we don't really want that, because we want this to alternate back and forth, right? So we're going to reset the processor and add just one more instruction here. And that's going to be a jump instruction. So for any of you who know BASIC, this is basically just going to emulate the go to instruction, except instead of going to a labeled line like 20 go to 10, that sort of generic thing, instead we're going to go to an address, because jump jumps you to a program counter position. So you can see when we reset this, it follows the reset vector to 8000. And that's the start of our program. So what we really just want to do is loop back to the start of our program in order to make this marquee effect keep on looping, because then it'll go back to here, read this, it'll perform all these operations, it'll get back down to the jump and go back up. So we need a jump instruction, and that's going to be under control, I believe. And here it is, it's 4C. So we get out our jump instruction, and I put it in. And if we pay attention here, you notice that the addressing mode for jump is A, just like the addressing mode for store A is A. So we're going to put in these numbers in the exact same way, just going to jumping to that reset vector. So let's clear it out and make a 0. And then right here, our reset vector is 80. So we're going to put in a number 80. Now we're all set. So that's our program. Let's upload it to the EEPROM. Now that it's in the EEPROM, we can reset our computer a little bit, and if we take a look, then hopefully we will, when we start running the program anyway, we'll get our usual A9 55 8D0060 stored out to port B. We repeat this, so we've loaded in AA, then 1, 2, 3, and then it should change our port B. And then on this next instruction here, we notice it got opcode 4C, and so it's jumping, right? So at this jump then, if we tick it one more time, when we get to opcode 4C, our jump instruction jumps us back to 0080, or 8000. And so what happens is when we read that, we read the operand low is the 00, and then the high is the 80, just like that, and then it puts them together to make 8000. And so then it puts our program counter, which we see is what's been incremented in this entire time, back to 8000. And so if we continue just ticking our CPU, you'll see that port B switches back, and then port B switches back again. So in fact, if we set our clock speed to like pretty fast and we run it, you see how it's flashing really quickly. Now you can see it just working through these opcodes until it manages to switch things back and forth. And so you can see some really common numbers here. It's counting from 8000 all the way up to 8000C, which is obviously this being 8000, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. And so because it gets all the way up to C, C is the last program counter right here in hex basically for it to read. We can see the A register switching between 55 and AA, which is those two values there. What else can we see? If we pay attention down here, our opcode is switching between A9, 8D, and 4C. So could we have A9, 8D, A9, 8D, and then 4C is like the odd one out, basically. And then we can also see our operands changing. One other thing to pay attention to right here, and I haven't set this up quite properly yet, but notice how this thing keeps on changing back and forth, and when it's like this, it's 10100. Basically, it putting in these extra 2 zeros is just because of how it's not like padding the number properly. But basically, the reasoning behind this is the negative flag is turning on and off, and that's because in what's called 2's complement, we have stuff like 55, right? If we put that into binary and turn that up one, in 2's complement, this very last bit of your byte represents if the number is negative or not. And so therefore, what you would have is like a normal number. Say we went, it would be like, let's put in like 42. Let's put in like 42 decimal, sure. So our normal numbers here that are positive, right? They would all be 0 for that first one. But if we wanted to put in a negative number, it's basically anything above 127, I think, or maybe like 128 and up, depending on how you look at it. So 127, if we put that in, that is basically the very like highest number that we can represent. I put that in wrong in hex, not decimal. But basically, that's the highest number that we can represent with that last bit still being 0. And so if we then increase that to 128, well, now our next bit turned into a 1. And what that means is then it means it's negative. So 128 then, basically at that point we would loop all the way back around to the negative numbers and keep counting back up. And so Because of this two's complement, the processor keeps track during certain operations of if something is negative or not. And so it turns out during our A9 operation, and maybe even during the story, I don't know off the top of my head, even though I programmed that, during the operation, it checks to see if the very last bit of the number, so let's go 128, need to do 128 decimal, keep forgetting there. It checks to see if that like 7th bit, if this is the 0 1 2 3 4 5 6 7, if that 7th bit is a 1 or not, and that's how it determines if it's negative. So you can see basically it's saying it's negative sometimes and not negative other times. And the reasoning behind that is if we put in 55 and we look at it, well, that one's a 0. And if we put in AA and we look at it, well, then our 7th bit right here is a 1. 8th bit, 7th, 0 index, whatever. But it's a 1, and so that makes it negative. So that's why that's happening. And so you can see our processor is ticking every 0.1 seconds, which is quite fast. So 10 times per second. It's a 10 hertz processor right now, which is actually not a very fast processor at all. It's very slow, but this is great for debugging, and it lets you see what's going on here. And obviously, if we wanted, we could like slow this thing down a little bit, like all the way down quite a lot, and now you can see that our program counter is ticking up much more slowly. It looks like right around every 1 second, then our program counter increments, and so you see it changing much more slowly there as well. We could also stop the clock and go back to ticking it manually like this. And obviously every time we tick it, it would get a new program counter. And eventually going through this enough, it switches. So that's our very simple program that lets us create this marquee effect on the processor. And this is kind of the idea for what a tutorial might be for this processor as part of like an independent study thing. Obviously, when you're actually doing this, the CPU would not just be like these blocks in front of you. You would be able to see like a lot more details of what's going on between each part and even inside the processor itself. It might be on like the table right here. But you can see this sort of like control center for the processor is a decent way to debug everything and kind of see what's working and what isn't in order to build this system.